So this is the first lecture on cellular networks. And so we're going to talk about what the mobile radio telephone service was and how it started off as mobile telephone services, and then how the cellular phone systems actually work and how they made it more advantageous than the mobile radio telephone service. Then we're going to talk about the trade-offs when determining the size and the number of cells within a certain service area. Now, the first mobile radio telephone service came out in 1946, and this was in St. Louis. And it didn't last very long because it had limited frequency spectrum allocation from the FCC, which meant that you're going to have limited number of channels that you could allocate to mobile users and therefore limited number of simultaneous calls. And so in this model with a mobile telephone, radio telephone, it had a single mobile telephone broadcast antenna somewhere centrally located. And it would have to use the lower frequencies, in this case 35 megahertz range, mainly because we know that the higher the frequency, the more the attenuation. So if you choose a lower frequency, you're going to have longer distance, less attenuation, and your reach is going to be much further. And in this example, we're going to just say that we have 20 half-duplex channels that have been allocated to us. Now, there were a little bit more in the St. Louis, the actual St. Louis service, but we're just going to go with 20 so that we can make a comparison with how cellular structures would actually operate in this same environment. So if you have 20 half-duplex channels, of course you need one channel for transmit and one channel for receive if you want a full duplex call. So then that means you only have 10 full duplex conversations that you can have simultaneously in the operating area. So you're very limited in the simultaneous calls. So because you're limited, this kind of results in very poor return on investment for the service provider as well as the mobile user who's trying to use this service, who's going to have to pay a lot of money because of the fact that there's going to be a very limited number of subscribers that can be supported. And you also have RF shadow areas. So if you think of a single antenna and you have this antenna that's trying to reach every single part of a city that has a lot of buildings, of course the buildings are going to obstruct line of sight and you're going to have reduced signal strength. So what you have is signal strength that is very non-uniform across the entire operating area. And then lastly, you have a single point of failure in that if the single broadcast antenna fails, then the entire mobile telecommunications for that area also fails. So obviously mobile services depended upon very limited frequency spectrum. And so therefore the Bell Labs in 1947 realized they had to come up with a new concept. And the concept that they came up with was the cellular concept. And the cellular concept was all about taking a surface area like shown in the solid line and breaking it down instead of a single large broadcast antenna, have several cells with broadcast antennas in the center of them. And so by doing that, you could actually, if you look at cell 1 and cell 4 here, you can use the same frequencies in both of those cells because they're geographically separated and you don't have to worry about co-channel interference. So in 1947, they ran into a few complexities that they just couldn't get over. The first one was the fact that they took their service area and they divided it into separate cells, each cell having a radio tower. And as a result, you had to somehow create these separate cells and turn it into a single network. Not only that, but you had to also take all those cells and they had to come into a mobile switching center so that they could be connected up to the wired telephone system. The other and probably bigger problem is that you had mobile users. And as a mobile user can move from any cell to any cell, you had to be able to follow that user and provide uninterrupted service regardless of what cell that user was on. And so this became such a technical hurdle that they decided to just go ahead and shelve the concept until technology kind of caught up with the idea. In 1973, with the advancements in computing and solid-state circuitry, Bell Labs and Motorola successfully demonstrated the cellular concept. And so this was where cellular services actually began. And then following in 1981, FCC allocated two 800 megahertz bands for cellular communications. So let's delve a little bit deeper into the cellular concept. And so on the diagram on the right here, we see that we still have our service area divided into 4 large cells. But this time what we're going to do is we're going to identify a cluster of 3 cells. So here's cell 1 of our cluster, 2, and 3. And you can see that the channel assignments, and remember we're going to use the same channel assignments as we did with the single antenna case, that we have 10 full duplex channels. And so we're going to say full duplex channels 1 through 4 is in cell 1. Cell 2 has full duplex channels 5 through 7, and then cell 3 has channels 8 through 10. And so all of the cells are going to have overlap areas with each other, and so therefore we don't have to worry about co-channel interference because they're going to be on different channels. So they can overlap and there's not a problem. Now, this is called a cluster, and it's a repeating pattern that we could put throughout the service area. So if we want to reuse some of the frequencies, let's say we're going to put another cell 1 over here, and of course it's going to use channels 1 through 4 as well. We can do that because there's sufficient separation between those two cell 1s that we don't have to worry about co-channel interference. And so this way we can actually increase the number of simultaneous users within the service area. So let's say here we have our cluster size of n equals 3, a pattern of 3 cells per cluster. And then, like before, we had a total number of full duplex pairs, which is going to be represented by k, and in this case we have 10 equals, or k equals 10. The number of simultaneous calls per cell is obviously going to be the total number of channels divided by the cluster size, and so for each one of these cells we can support 3.33 calls. So of course we're going to round it off and we can just simply say that we support 3 calls. And so if we want in the entire area to determine how many simultaneous calls we could actually have, we can say that we have 4 cells times 3.33 calls per cell, and now we have 13.32 calls, simultaneous calls that we could support in our service area. Now if we compare that to the previous slide where we just had a single antenna, we could only support 10 simultaneous calls. So by using this cellular concept, now we've increased it by 3.32 calls. So let's say we wanted to dramatically increase the number of simultaneous calls in our service area. And so we're going to still stick with a cluster size of 3. And of course, all we have to do is decrease the size, because if we decrease the cell size, we can increase the number of cells within the cell area, our service area. And so because we just don't want to, we want to avoid co-channel interference, you can see that all the numbered cells are going to be at least separated by 1 cell. So we don't have to worry about any overlap area, therefore no co-channel interference. Now in this pattern, of course, we're going to have 38 cells in our entire service area. We're still going to use a cluster size of 3, and we still haven't increased the number of available channels to us. It's still 10. And so we know that we still have 3.33 calls per cell that we can do in simultaneously. And so now the total number of calls that can be supported within our service area is essentially going to be 3.33 calls per cell times 38 cells, or now 126.54 simultaneous calls within our service area. So that's much, much better. But you also get a few other benefits, and the other benefit you get is that you have a smaller cell, and the reason why you have a smaller cell is you reduce the transmit power. Of course, your signal is going to attenuate faster, and so the cell gets smaller. But that also means that the mobile user will be closer to a cell. And if the mobile user is closer to the cell, the battery life of that mobile user's device is going to be much longer. So now you have mobile phone sets that are going to last much longer than if the cell size was large. Now the biggest drawback to all of this is that with 38 cells you have much greater complexity. Number one, you're going to have users changing cells more often. You're going to have more cells that you have to connect together to create a single network, and all of that is going to have to go back to some kind of mobile switching center. So let's summarize real quickly. If you decrease the cell size, then you're going to increase the number of cells in your service area, and by doing that you can increase the number of simultaneous calls. And this has the benefit, obviously, of improving battery life for your mobile user. However, it's also going to increase complexity of your service, because now you're going to have many more cells that need to be interconnected, and you're going to have a lot more handoffs as mobile users move from one cell to another. We saw how decreasing the size of the cell and increasing the number of cells within a service area increased the number of simultaneous calls we could support. But what would happen if instead we changed the size of the cluster? And why would we change the size of the cluster? And so let's compare a cluster size of 3 with a cluster size of 7. So on the left, with a cluster size of 3, of course, it's what we saw before. We have the first cluster in blue, the second cluster in red, and then a third cluster, the beginnings of a third cluster in green. And of course, we know that if we have only 10 full duplex channels available to us, then we're going to have only 3.33 calls per cell out of the 7 cells that we have. And of course, in this case, it's going to be 3.33 times 7, or we could actually support 23.3 calls. Now let's change, using the same numbers as far as the availability of full duplex numbers. Now we're going to, and cell size, we're going to say cluster size of 7 instead of 3. And so all these cell sizes are relatively the same, but now what we're going to do is we're going to allocate our frequencies to 7 cells, a 7-cell repeating architecture. And so this time with a cluster size of 7, we see that per cell we only get 1.43 simultaneous calls per cell. We still have 7 cells as with the cluster size 3 example, but now we only have 1.43 times 7, or 10 calls that we can actually support. So as the cluster size actually increases, the number of simultaneous calls decreases. So why would we even care about going up higher if that's the case? And the answer is pretty simple, because if you see here's a cell 1 and here's a cell 1, and you can see we have essentially a 2-cell separation between 2 cells that are operating at the same frequencies. So in the case of a very noisy environment, or if maybe you have unpredictable propagation of your channels, if you only have 1 cell difference like you would in a n equals 3 cell cluster, then you might still have interference. And so you may have to separate those cells that are operating on the same channels. And so you would increase the cluster size, and in this case we've increased it to the point where now we have much more separation between those cells operating at the same frequency than we do with a smaller cluster size of 3. So that's one of the reasons why we would increase the cluster size. So just in case it was confusing, on this picture on the right here, we can see that we have 7 cells in the surface area. This cell is not counted. This cell was just, I placed it there so that we could see a separation if we had a repeating 7-cell segment that actually fit in the surface area. So to kind of summarize like we did before, if we increase the cluster size n, then we decrease the number of simultaneous calls, but we increase cell separation. So we saw that if we decrease the cluster size n, we can actually increase the number of simultaneous calls within the surface area. And so it goes to reason to say that we would like to have a cluster size of 1. And a cluster size of 1 means that every cell is going to be operating on all of the frequencies that are given to the service provider. And so this is called the intercell interference coordination, where we actually achieve an n equals 1 cluster size. Now, in order to do this, what this coordination means is that every base station has to be in contact with adjacent base stations. And so this could be a coordination of tracking mobile users that happen to go into an overlap area, and between the 2 stations that control that overlap area, they must coordinate and, if need be, change a mobile user's frequency channels. Obviously, this increases complexity, but because of the high demand of subscribers, we see this actually implemented in 4G and 5G cellular systems. We have some generic terms for cell sizes. We have the macro cell, which is approximately 60 miles in diameter. Then we have a microcell, which is about 4.3 miles. And then we have picocells, which can be just a few blocks. And the smallest are all femtocells, but femtocells are a little bit special. You find them on floors of buildings, or even a section of a floor within a building. So let's see what's so unique about a femtocell. So let's say you had a building and this was like a hotel. And of course you're going to have several floors, and maybe on one of the floors you have a femtocell. And that femtocell is going to operate on cell frequencies. So you'll be able to use your smartphone and communicate directly to the femtocell that happens to be serving the floor or the building that you're in. Now, the nice thing about the femtocell is the femtocell, instead of having to connect up to the mobile switching center of the cellular system, will actually use the building's broadband connection. And this would be a broadband connection to the internet. And so this broadband connection goes through the internet and then goes to the mobile switching center of the cell system, which is the wired portion of the network. So this would be the cell provider. So what are the benefits here? Well, first of all, the benefit to the building owner who has to essentially ferry all these calls through his broadband connection to the internet to get to the cellular system is going to benefit, because they're going to have great cellular service along all of its floors within the building. Then the service provider benefits because of the fact that it doesn't have to worry about the backhaul from the femtocell through its own system to the mobile switching center. It will use the path through the internet, and then the internet will connect up directly to the mobile switching center. So benefits for both the service provider as well as the organization requiring femtocell connections. So as a service provider, you're going to have a limited spectrum allocation from the government. So the question is, how do you increase subscriber call capacity? And there's several strategies you can actually use. One is to add more frequency spectrum by asking for it. Of course, this is going to be very long-term, probably involved lobbying to the administration. It's also more strategic than it is tactical, so it doesn't really help with any kind of current shortfalls that you might have. Another way is to pool all of your channel frequencies, and because the call volume may differ during different times of the day in different parts of your area, being able to dynamically assign those frequencies wherever and whenever they're needed would actually help balance out the call capacity. However, this is going to increase complexity. You can use a frequency borrowing strategy, and in this case, it's usually done between adjacent cells. And so if you have two adjacent cells, and let's say one's in the restaurant area and the other one is in the business area, during the daytime when the business is in full swing, of course, they're going to need most of the allocation of channels. And so therefore, the restaurant district may not be all that busy. So the restaurant district sends over its frequencies so that there's more frequency channels that can be used during the business hours. But of course, after the business hours, when everybody starts leaving, they may be going towards the restaurant area. And so now the restaurant area needs more frequencies. And so therefore, there's another exchange in which those frequencies are then allocated from the business area back to the restaurant area. So doing frequency borrowing is one way. Of course, it's going to be between adjacent cells, and it could also increase complexity. You can decrease the size of your cells, which means that you're going to have a lot more cells within the service provider area, and this is called network densification. Of course, this also leads to complexity. And we talked about femtocells, in which femtocells are even just smaller cells that are maybe the size of a floor in a building. The nice thing about it is that we're going to use a subscriber's broadband connection to the internet as a backhaul. So this alleviates some of the traffic or some of the responsibilities of the service provider. But however, once again, this is also complex. And then you have technical solutions. And some of these technical solutions drive towards greater spectral efficiency, greater efficiency of the use of the channels that you have. And some of these might be CDMA, which is a spread spectrum technology, OFDMA, which is orthogonal frequency division multiple access. Of course, using M-Mary modulation techniques, and then MIMO, or multiple in, multiple out spatial antenna arrays. And then finally, We talked about being able to reduce the cluster size to an n equals 1, meaning that we're going to have ICII operating, which, as we mentioned, also increases complexity. In this section, we talked about the mobile radio telephone service, which was the first service out in St. Louis way back in the 40s, and we saw the many drawbacks of just having a single antenna, and that the need for a cellular concept to actually increase subscriber numbers in an environment where there weren't that many frequency channels that could be allocated to the mobile users. Then we talked about the benefit of the cellular concept and the impact of the cluster size and the cell size when we're actually implementing cellular concepts. And then we talked about technical ways to improve the support to increased subscriber numbers. We're going to take a look at what a typical cellular architecture looks like. What are the components that make up this cellular system, and what happens when mobile devices are turned on and when a mobile device initiates a call. So what we're going to do to try to understand what the cellular architecture looks like is use a representative model, and this is going to be the 2G GSM system, which stands for the Global System for Mobile Communications. And so this is a very generic type of system. As you can see, we're going to always have some kind of radio access network, and so in the GSM's case, this is going to be called the base station subsystem. So this is where the radio towers that create the cells will be. This is where the mobile systems, mobile stations are going to be located that communicate to the radio system. And of course, you're going to have some kind of backhaul to a wired network, and this is represented by the network subsystem, or NSS. And this is really where all the brains of the cellular architecture resides in. This is where the mobile switching center is in connection to other networks such as the internet or the wired telephone system. So let's take a look at each one of these devices or components. So let's first talk about the mobile station. And the mobile station is sometimes called the mobile equipment. And as you can see here are mobile stations, and that's essentially our mobile telephone communicating with the base station tower. And along with the mobile station comes two numbers. One is called the IMSI, and the other one is called the IMEI. And the IMSI stands for the International Mobile Subscriber Identity, which describes your account with the service provider, and it's usually located on a SIM card. And the SIM card is the subscriber identification module that's actually on a card that slips into the telephone. The other number is the IMEI, which stands for the International Mobile Equipment Identity, and that identifies the hardware or the actual phone itself. The mobile stations will communicate to the base transceiver station, which actually creates the cell through an AirLink or an RF link. And it's this RF link that will be frequency division multiplexing, time division multiplexing, code division multiple access, or orthogonal frequency division multiplexing. And there's actually two different types of channels that connect the mobile station to each base station. The first one is a traffic channel, and these are the channels that will carry the voice and data between the cellular service and then the subscriber. And then you have control channels, much like the control channels that we saw with the PSTN, in that this is where control and signaling occurs, and these are much more narrow channels that are shared by multiple users. The mobile stations are connected up to a base transceiver station, also called a base station. And the base station consists of the antennas and the transceiver equipment that makes up the cell. And then these BTSs, or base stations, are going to be aggregated through what we call a base station controller. The duties of the base station controller are there to aggregate the data from the base stations. It also reduces the connection and processing for the MSC because it actually takes on some of the duties of the MSC, such as allocating frequency channels to the base stations, tracking mobile users and handoffs between the base stations that it controls. Then it also coordinates MS calls, and then ensures that the control and traffic channels serve the mobile users. And finally, between the base station controllers and the network subsystem, you have backhaul links. And these backhaul links are pretty broadband links that allow all the information coming in from the base station subsystem to enter the mobile switching center. The base station subsystem is essentially a radio access network. So let's just go ahead and write this. And this is very similar to when we were talking about Wi-Fi, because with a Wi-Fi network, you'd have your wireless device connected up to an AP of a Wi-Fi system, and you know that behind that Wi-Fi AP is going to be a wired network that gives you all the services and connections that you need to other networks. Well, it's going to be the same way with the cellular system, that the radio access network will give you access to the network subsystem. And the network subsystem is the wired network behind all of the towers, cellular towers. And it's got a lot of capability, and the biggest capability is going to be the mobile switching center, because this is where calls made to and from a mobile station can be made. It's going to have the smarts to see that if there's an outgoing call that needs to go out to the internet or the PSTN, it will direct it towards that gateway. And likewise, if you have a call coming in from an outside network, it will redirect that to your mobile station. Regardless of where you are, it'll go and find where you are. And it uses some of these databases in order to do that. So let's go through some of these databases that are down here. First, we have the home location register, and this is where we have permanent and temporary subscriber information located in that database. And then we have the visitor location register. And so this helps to track the movements of the subscriber throughout the cellular system. And so that way, if there is an incoming call from, let's say, a wired network like the PSTN to your mobile station, it will find where you are through this VLR. There's also Authentication Center, and so when you turn on your phone, the first thing that the cellular provider has to do is to authenticate that you are indeed a subscriber. If you're not, then you don't get service. If you are, then you do, and it's done by this Authentication Center, or this database here. And then finally, you have an Equipment Identity Register, and this is where all the IMSIs and the IMEIs are kept. And then finally, as I had mentioned, we have gateways which can connect the cellular provider to external networks. So let's talk about handoffs between cells. So let's say in this cell and in this cell, you're both going to the same base station controller. So if a mobile user moved from this cell to this cell, then of course the base station controller is going to handle that handoff. However, if instead this user were to go into this cell here, you can see that they don't share a base station controller, and as such, the coordination has to now go all the way to the main switching center. So how does a cell handoff happen? Well, let's say this is cell A, and this is going to be cell B, and we have a person that's actually operating in cell A, and so they're a mobile system, and they're going to have a certain power signal strength that the BTS is going to detect. And so if this user starts to begin to move into B's cell, then the signal from the mobile unit is going to start to decrease to the point where it's going to say, well, he's out of my cell, so I no longer have responsibility for that mobile user. On the other hand, B will see this mobile user coming into its cell, and it's only going to be getting stronger and stronger. So now it knows that, well, I need to provide service to this mobile user that has transitioned from cell A to cell B. And so a lot of the handoffs are going to be based on the strength of power to and from the mobile system. There's two major ways that a cell can actually hand off user to another cell, and that's through a hard handoff where the connection is actually broken before one is reestablished with the new cell, and then a soft handoff in which the connection is kept with both cells until one takes over the connection completely. And so let's take our example of our individual moving from cell A to cell B. Well, with a hard handoff, as soon as he's out of range of cell A says, I'm no longer responsible, and then it has to wait until B essentially picks up that user as it goes across. And so this is the hard handoff, and that's fine with analog communications, but when we talk about digital communications, it's problematic because you lose data if the connection is lost and has to be reestablished. So let's take a look at a soft handoff, and the soft handoff essentially says that as the user is leaving cell A maintains contact until it knows that cell B has actually accepted that contact and is providing service. And once A knows that B is providing the service, then A will go away. And so this is much better for digital communications because you don't lose data and you're assured of a smooth connection between the cells. So let's talk about what happens when you first turn on your phone and when you make a phone call. So your mobile station is turned on, and as soon as that mobile station is turned on, your phone will start to scan all of the nearby control signals coming from the base stations. And typically, it'll select the strongest control signal, which means it's going to select the base station that has that signal. As soon as that signal is established, a handshake takes place between your mobile system and the main switching center. And the main switching center will want to validate who you are, so it's going to look at the home location register, look up your subscriber information, then it's going to go to the authentication center to make sure that you can authenticate as a user or a subscriber, and then your position is going to be marked through the visitor location register so that any outgoing or incoming calls, the phone service will know where to contact you. So now let's talk about what happens when you want to make a call. So the MS makes a call, and that call is going to be over a control channel. And so that call with the destination phone number is going to be sent to the BS. The BS will actually forward that to the main switching center. And the main switching center will look at its VLR records to see if that recipient is within the service provider network. If it's not, then it must go out to the gateway and then go to an external network. If it is within the service provider network, then it goes to the BS where the recipient last was known, the recipient's last location, and then the BS will send its own paging information on its control channel to all the users within that cell. Once that call is accepted by the recipient, then MSC actually sets up a real traffic channel, and of course the control channel will continue to monitor the quality of service on that channel, and then once that call is terminated, then the MSC will free up those channels and then of course complete a billing cycle. In this section we talked about the cellular architecture and the common components and their purposes, and then we also went over the mobile connection process as well as cell handoff. In this section, we're going to be talking about the technologies that help to shape various cellular generations and how the technology and innovation help to meet subscriber demands. We'll see what the role of the ITU in shaping global interoperable cellular services was, and then we'll delve a little bit into the 4G LTE advanced architecture. In this diagram, we see the generations from 1G to the current 5G and how they changed in some of the technologies and some of the ways they offered new subscriber capabilities. 1G was, of course, all analog, so the only analog cellular system that we ever had was in the 1G area. And everything beyond 1G, when we talk about 2G to 5G, obviously are digital, as we can see here. Now with 2G, because we went to digital, we still had some incompatibility issues. And so this is where ITU's IMT 2000 came in. And IMT stands for the International Mobile Communications in the year 2000. And so this was an attempt to try and standardize and make all cellular offerings more interoperable. And so you can see that they've gone through some capabilities here. Mostly digital going into spread spectrum technologies. And then finally, we had another ITU IMT Advanced. And IMTU Advanced introduced OFDM. It introduced a packet switching capability. And then, of course, for 5G, which is the capability that's currently under development today, IMT 2020. So if we look at the generation from 1 all the way out to 3.5, we see that this was really kind of based on the circuit switching concept. And everything 4G and beyond became a packet switching concept. So what does this mean? This means that in the circuit switching concept, The mobile telephone was essentially just that, a telephone, an extension, a wireless extension to the wired telephone service. But as soon as we got into 4G and beyond, this became packet switching, which meant that we were more data communications. We were more about IP and TCP connections. And so this was a dramatic change between 3.5G and 4G. And so let's go through some of the generations and talk a little bit more about some of the technologies that were involved. First generation cellular systems came out in the 1980s. And of course, all the traffic channels were analog. And so as an analog system, the only way that you could aggregate calls would be through frequency division multiplexing. And in fact, the only way that you could allocate channels to specific calls was through frequency division multiple access. And what this meant was, per call, you would actually dedicate whole channels to support that call. And of course, that leads to poor spectral efficiency. So obviously, the number of calls they could handle, given the limited amount of spectrum that was provided or that was given to them, was very minimal. Now, of course, the digital control channels existed, modulated through frequency shift keying. Now, one of the other features of an analog system is that it's very difficult to encrypt analog signals, and so therefore most service providers didn't even try. And therefore, calls were vulnerable to eavesdropping. And in a lot of cases, because of the fact that there was a lack of privacy encryption on the calls, all you really had to do is get a scanner, dial into the correct frequency, and you can listen to anybody's phone call. Not only that, but because of the fact that all the frequency using frequency division multiplexing were narrowband channels, of course, we talked about how radio frequency interference and noise affects narrowband channels much more than a spread signal. So, of course, with 1G systems, they were very vulnerable to radio frequency interference. And so some examples of the standards that were used was AMPS, which was in the 850 megahertz band, and that was predominant in the U.S. In Europe, TAX was predominant, and that was at 900 megahertz band. And in the Nordic countries, we had NMT, which used actually 400 megahertz and the 900 megahertz bands. And of course, none of these systems were interoperable. As the popularity of mobile telephones grew, there needed to be a way to actually increase the number of subscribers, but of course the frequency spectrum that was offered to them was still limited. So 2G decided that they needed to go to all digital channels, so that digital traffic channels. And what they did was they would still have, in many cases, the frequency division multiplexing structure where they had channels, but then on each channel, since they were digital, they could actually use time division multiple access, and by doing that, they could actually assign slots to calls, which meant that for a single channel, you could actually support multiple calls. So this really was a way to increase the number of subscribers, increase the number of calls available. Another 2G effort was the first direct sequence spread spectrum technology, which was code division multiple access, or CDMA, and that was based on a Qualcomm standard called IS-95. So obviously, even the use of TDMA, but even more so the use of CDMA, offered much better spectral efficiency. Of course, that also came with better security because now you had an ability to encrypt your information. And then, of course, we still have the digital control channels. So certainly by the second generation, we were completely digital at that point. Now, some of the examples were, this was when the GSM, or the Global Systems for Mobile Communications, first came about. And originally, they came up with the FDMA TDMA structure. So they used TDMA slots over FDM frequencies, which multiplied the number of calls they could actually serve per channel. But one of the neat things that they offered was this thing called GPRS, which is the Global Packet Radio System service. And so GPRS was on just one or two slots within the TDMA structure. It offered only about 21.4 kilobits per second, but what it offered the users is an ability to have a persistent connection to the internet. Now, of course, at 21.4 kilobits per second, that's not going to be a lot of speed, but it was enough to go and check on email, maybe do a little bit of messaging. And of course, this became so popular that GSM increased their capability to what they call EDGE, which was the enhanced data rate for GSM evolution. And that increased the data rate threefold up to 68.4 kilobits per second. So essentially what they did was they used more time slots to support the GPRS, which was actually packet switching within the time slot to connect up to the internet. Now, this was predominant in Europe, and in the United States, we had Qualcomm IS-95 or CDMA-1. And so CDMA was a spread spectrum technology, more efficient than TDMA, and it replaced the digital amps because in 2G, when in the U.S., when the analog 1G systems were digitized, they wanted to keep the same structure, the same frequencies, and so all they did was they digitized the frequency channels. So CDMA was a departure or a big advancement from just digitizing the channels. It was where they were going to place direct sequence spread spectrum. And of course we know that direct sequence spread spectrum gives us better spectral efficiency and gives us more immunity to RFI, and of course made it very difficult for anyone to eavesdrop or intercept calls. So you can see from this timeline, we had a 2.0 and a 2.5G separation. And it was 2.5G that actually introduced some packet switching through GPRS and EDGE, and where CDMA-1 was introduced spread spectrum technologies and higher spectral efficiencies. And this was about the same time that ITU got involved, and the International Telecommunications Union came up with requirements, which was IMT 2000, or called the International Mobile Telecommunications 2000. And these requirements were intended to make systems more interoperable, more standardized. And as a result, some of the requirements, they wanted to support higher data rates. They wanted to be able to support not just voice, but also data, as was proven out by GPRS and EDGE. They wanted to have seamless roaming so that you could go outside of your subscriber service area and actually roam with other service areas, so extend your ability to use your telephone. It had to be affordable, obviously, because it should be something that any common man could actually use. Had to be backward compatible. And the reason why this is they wanted service providers to adopt the new 2.5 and 3G requirement. And in order to do that, you had to reduce the cost as much as possible. So just like when we were talking about Wi-Fi and how we need to make backward compatible because we're talking about infrastructure, the cellular systems went the same way. And they said that we have to be backward compatible with previous generations so that we can continue to evolve the system in a reasonable manner. Of course, they wanted modular design, and they recognized the idea that data rate is going to be based on the mobility of the user, whether it's fixed, slow-moving, or in a high-speed vehicle. So some of the choices that IMT 2000 made was that they were going to adopt CDMA, as well as, in some cases, TDMA, which was mostly GSM. Two of the dominant 3G standards were the UMTS and CDMA 2000. So UMTS, which stood for the Universal Mobile Telecommunication System, was a successor to GSM. And they used wideband CDMA spread spectrum technology, and they renamed the base station subsystem, which was a radio access network, they renamed it UTRAN, which stood for the UMTS Terrestrial Radio Access Network. Now in North America, where CDMA-1 was predominant, it was replaced by CDMA 2000, also a spread spectrum technology. And even though there was a commonality between WCDMA and CDMA 2000 because they both used CDMA, they were not compatible. When 4G came around, of course, ITU still wanted high compatibility between all the cellular services globally. And so they came out with IMT Advanced requirements. And so the IMT Advanced requirements emphasize global compatibility between fixed and mobile services, an ability to interoperate between cellular systems and providers, a commonality of wireless user equipment so that subscribers didn't have to buy their equipment from the service provider. They could go anywhere and purchase that. They wanted to have worldwide roaming as well as enhanced bit rates. And this is probably one of the biggest requirements, was that it was a shift from circuit switching to the packet switching concept. So this is where with the advent of the smartphone, that the cellular systems turned from just an extension of a wireless telephone to something that was more of a handheld computer connected up to the internet. The other big innovation was the fact that they abandoned in 4G spread spectrum technology in the form of CDMA and adopted orthogonal frequency division multiplexing, because OFDM was more spectrally efficient than direct sequence. Now, some of the examples of 4G systems were, of course, LTE and WiMAX. And so when LTE and WiMAX first came out, they did not meet all of the IMT advanced requirements. And as such, LTE became LTE Advanced in 2011, and WiMAX actually became WiMAX 2. And so these two standards were actually compliant with the IMT Advanced or 4G standards. Now, these two standards, LTE and WiMAX, were pretty compatible with one another, and so one really didn't have a big advantage over the other. However, over time, LTE did win over a lot of the market share, and it became the standard of choice. And the reasons why some say in the industry is because that LTE provided a better evolutionary path to 4G than did WiMAX, which was a dramatically different architecture. And another 4G innovation that I want to mention is MIMO antenna, spatially arrayed antenna system, multiple in, multiple out. So today, the current competition is between service providers in the 5G arena. And so, of course, ITU came out with IMT 2020 requirements, and that was published in 2017. And so it called for asymmetric downlink and uplink data rates. So downlink at 20 gigabits per second, uplink at 10 gigabits per second. So they're asymmetric, which is something that you would expect when you communicate up to the internet. Also, a requirement for improved spectral efficiency, ability to support millions of devices per square kilometer with low latency. So here they're addressing the fact that the Internet of Things are going to be big in the coming years. And efficient power usage of the radio access network. So we want to start looking at low energy, wake, and sleep cycles. So here, once again, it's that these devices might be part of IoT. They may be battery operated. So we want to not have them expend all of their battery power just because they're part of the network. So this is definitely directed towards IoT. And of course, increased bit rates based upon user motion. So here again, taking the previous IMT Advanced ideas of separating all the motions at the speed of the mobile user. So 5G adopts a lot of the 4G technical innovations, such as OFDM, also adopts MIMO and the packet switching concept. And of course, because we have limited frequency, we have to get allocated more frequency. So 5G cellular systems are going to be allocated other bands within the spectrum for use for 5G cellular systems. And this is one of the ways that we could actually dramatically increase the amount of data that we transmit up and down in communications and to the internet. Now, even before IMT 2020 was published in 2017, there were several service providers that had already mentioned and publicized that they were going after their own 5G standards. And some of these companies, such as AT&T, Verizon, South Korea, KT Telecom, Slovenia, and Mobile Telesystems, both within Russia, and many, many other service providers around the world, understand that if they come up with a popular standard, then they become the de facto standard that all the other service providers will have to abide by if they want interoperability. So despite the efforts of ITU and the IMT 2020, it still remains to be seen whether 5G can ever achieve its goals of true interoperability between all the cellular system providers around the globe. And finally, let's take a look at the 4G LTE architecture. And the reason why I show this is because all the architectures that will be within 5G and beyond are still going to have the same elements. Sometimes the nomenclature changes, but the technology doesn't. And so if you understand the technology and how the radio access network works and the fact that you have to have a wired network behind to provide the connectivity to services as well as to other networks, then despite the name changes, you should understand the cellular system and how it actually operates. So we're going to go and take a look at this LTE and go through the pieces. So let's start with the radio interface technology. And so radio interface technology is essentially the radio access network. And it's going to use time division duplexing, which is full duplexing based on transmit and receive time slots, as well as frequency division duplexing, which is full duplex using transmit channels, frequency channels, and receive frequency channels. Of course, we know orthogonal frequency division multiplexing, which is going to divide the operational spectrum into overlapping subcarriers that carry our data in parallel. Then, of course, each one of those subcarriers need to be modulated. So we have different modulation techniques, such as a quadrature phase shift keying, and then, of course, M-Mary quadrature amplitude modulation, whether that's M equals 16, 64, or 256. We have carrier aggregation that's possible on 4G networks. And so carrier aggregation is essentially taking a couple channels, combining their bandwidth so that you have greater bandwidth. And so we know from Shannon Hartley that increasing the bandwidth will increase the capacity and bit rates. And then, of course, we have intercell coordination, interference coordination. And so ICIC, if you recall when we talked about cluster sizes, allows us every cell to use all the frequencies within the service provider network, not just frequencies allocated to them. And as such, you can increase the number of simultaneous phone calls that you want to support. Now, if we look at the architecture in the diagram for LTE, we can see that it has a lot of similarities with the GSM architecture, in that, first of all, we have to have some kind of wireless access. And remember, with GSM, we called this the base station subsystem. And so this is now in LTE just called the Evolved UMTS Terrestrial Radio Access Network, or EUTRAN. And of course, just like Wi-Fi, just like GSM, we have to have a wired network that supports the wireless access. And so therefore we have, in the case of LTE, an Evolved Packet Core, or EBC, which was the same thing as our network subsystem within the GSM network. And as you would expect, we would have cells that were created by base station towers, but now our base station towers are called eNode B, or EUTRAN node Bs. So this is essentially just a base station, and it's going to define the cell. It's going to have all the antennas and transceivers, and in this case, it's going to also communicate between cells for mobility management, ICIC, and load management. And so essentially it's kind of like a coordination between the cells. Now what's interesting now is that even with this system, you need to have both user traffic and signaling and control. And so in this case, we have S1U, which is going to be the S1 user plane, which is like the traffic channel that goes to the serving gateway that provides the actual traffic channel access. And so S1U is essentially the traffic channels, and then the S1C are going to be the control channels, or the S1 MME, that goes to the mobility management entity. And so you can see here that's control and signaling, user access, tracking, call setup, security, and authentication. And of course, it makes sense if these are control channels that it's going to connect up to some database that's called the home subscriber server, which is similar to what the HLR and VLR did as far as trying to authenticate users, looking to see if they are actually part of the system as a subscriber. And the last piece here is that we want to have the traffic go out to, in this case, the internet. And so we're going to have a gateway, just like we did in our other networks, where we're going to send our traffic through the gateway and then into an external network. So the bottom line of this exercise, looking at LTE, is the fact that if you take any wireless network, even a guided network, and if you truly understand the fundamentals of telecommunications, of the communications process, then you could break down and understand any complex network, despite the fact that there might be some nomenclature changes. In this section, we took a look at the cellular generations and the technical innovation each generation brought. We looked at ITU's efforts to standardize the cellular industry through IMT 2000 Advanced and 2020, and then we took a deeper look at the LTE architecture.